Familiar with the Simons Institute, I want to say a few words about it. It was founded in 2012 by a generous grant from the Simons Foundation, which continues to support this institute to a large extent. It's meant to bring together leading researchers in theoretical computer science from around the world, along with young stars of the future. And the kinds of research we do here are both looking at computation itself and trying to understand the nature of computation, but also applying the algorithmic lens to different subjects and seeing what insights we gain from that. So I want to thank the organizers of this program for putting together a great program. So Henry and others, and I'll hand off to them very shortly. I also want to thank the staff at the Simons. The event staff have been planning this for months, and you probably received multiple emails from them. So they've been the people responsible for making it happen up to this point. And then the IT staff and the videographers, AV staff, are really doing it today. A few do's and don'ts. One is that we do not allow any food or drink in this auditorium. There's an absolute strict edit. That's why the auditorium manages to maintain its pristine state until now. Please have your food outside. The plates and bowls, as Berkeley is an environmentally friendly place, the plates and bowls are compostable, and please find a compost bin to deposit them. If you want to protect your valuables when you're going out to lunch, which you do on your own, there are lockers near the restrooms on the far wall over there. And I guess the AV people will assist you in setting up talks and so on. So for those of you who are on X or Twitter, there's a hashtag that we'd like you to use when you're tweeting about this workshop. It's hashtag, it's up there, thank you, at Simons Institute. Enjoy the workshop and Henry.
Thank you, Sampath. So first off, I'd like to welcome everybody to Simons and to the workshop. Thanks you all for coming. It's very nice to see so many people doing coding and willing to come all this way to a workshop. I have a few announcements relative to the conference. One thing is we had a poster session scheduled, which we announced very late, unfortunately. So we're planning to switch that to what I'm going to call a lightning talk session. So if you or someone attending would like to present a 5 to 10 minute lightning talk on Wednesday during what was formerly the poster session, please email Christian and I by tomorrow night, and then we'll organize that. And then after that, we'll move, and some of the places on the schedule say open discussion. We'll move to the second floor if you haven't been there yet. And there's lots of whiteboards, and this is a great spot for open discussion. So that's the plan. There's also, I don't know if they've hit, there's a few updates to the schedule. So I'd say by within an hour or two, the schedule should be hopefully finalized for the week. We'll see. All right, and then now my next duty is to introduce our first speaker, Rob Calderbank, who of course needs no introduction. I will mention only that rather than waste everyone's time with these, I'll mention only that most notable National Academy of Engineering member and Shannon lecturer. So please take it away, Rob.
Thank you very much for the introduction. I'm experimenting with the volume. Is that maybe a little too loud? Should it be a little bit lower? Yeah, great. Okay. All right, learning to communicate. First thing I want to say about this talk is I should apologize. It's not a math talk. And so you might look at this talk and you might say, well, where did he hide the math? And the math is actually hidden in these two papers, which appeared in the Information Theory magazine. They have all of the mathematical details. So what's the context here? So we're starting in the wireless communication world. We're starting to think about 6G. And what's different about 6G is that the propagation environments are becoming more challenging. So what I've done here is I've arranged channels in order of increasing Doppler. So pedestrian channels, no Doppler at all. Terrestrial mobile, 300 hertz. Millimeter wave, maybe 3 kilohertz, and so And I would say that today we design wireless systems using mathematical models. So we say we're only going to consider so many paths. We're going to put constraints on the delays and the Doppler shifts. And what I would say is that this approach is losing ground as wireless channels become more complex and Doppler becomes more significant. And one of the themes in this talk is, might it be possible to operate model-free? And I'll explain what that means. But first of all, some context. Model-free is a question that we've asked before. I mean, we asked it in the 17th century. And you can think of Newton's laws of motion as model-based. And you can think of Kepler's laws of motion as being model-free, right? Because Kepler just observed stuff. What's changed since the 17th century? All our students know that machine learning is the most important thing ever to have happened in the history of the world. And of course, they're right. Certainly in the last 10 years, it's revolutionized image, natural language processing, bioinformatics. It's even starting to revolutionize mathematics. I mean, analysts used to think when they thought of functions, they thought of these really complicated function spaces like Bezoff spaces. And now they're starting to think of how well you can approximate a function with a certain class of neural networks. And so it's changing mathematics too. I do recommend this very short paper by Weinan which is talking about exactly this. It's a beautiful paper. It's only 2 or 3 pages long, but it's very nice. All right. The theme of this talk, or one of the themes, is that you should all be doing signal processing in the delay-Doppler domain. Let me put out an applied advertisement for that. Last week was Mobile World Congress in Barcelona. And there was a press release by Vodafone, which basically said, if you manage multi-user MIMO in the delay-Doppler domain, you can increase spectral efficiency by 50%. Now, if you're a carrier, that's a super big deal. Because as a carrier, you don't believe in IoT. You don't believe in all of these applications that are going to miraculously arrive and give you new revenue. You do believe that if you can increase your spectral efficiency by 50%, you can make more money. So it's grabbing a lot of attention. Anyway, so who's this person on the slide? He's called Philip Woodward. And he died in 2018 at the age of 98. And he was a very distinguished radar engineer, and he was a virtuoso clockmaker. And in 1953, this is like 5 years after Shannon's paper, he wrote this book about probability and information theory with applications to radar. And he had this really beautiful idea of what radar was. He says, radar, he says, you should think of it as a game of 20 questions with an unknown operator. How does that work? You have a radar scene, you send it a waveform, the operator acts on the waveform, you get a return, you get some information about the scene. It's a game of 20 questions. You're trying to discover the operator. And so he was thinking about, well, what waveform should you pick? And this isn't the waveform he picked, but it is the waveform in the time domain that we're going to spend a lot of time talking about. This is called a pulsone because it's a pulse train that's modulated by a tone. But it's similar in spirit to the waveforms that Woodward was looking at. All right, so here, first of all, we're going to be looking at doubly spread channels. So these are channels that shift in delay and shift in Doppler. And I'm going to argue that a pulse in the delay-Doppler domain is what you should use to signal on these channels. And I'll explain what a pulse in the delay-Doppler domain is. But here we have a picture where we transmit the signal X. It bounces off these reflectors. These reflectors displace the signal in delay, and they displace it in Doppler if the thing is moving. And I want to represent it like this. I want you to think about the reflectors as like geometric modes of the channel. What's a geometric mode of a channel? It's something that moves the basic pulse around. So if you thought about an LTI channel, which is what you'll teach, right? Pulses are geometric modes of LTI channels because the channel moves them about. And here, pulses in the delay-Doppler domain are going to be geometric modes of these doubly spread channels. And so here on the right-hand side, what I've just represented in a picture is how the propagation environment acts on the signal we transmitted. The height of these bars is the energy in the reflection, and the position is whether you moved in delay or you moved in Doppler. And we're going to think a little bit of radar as we go. And so thinking about waveforms, if you send a time domain waveform, you don't actually get any information about Doppler, so you're ambiguous to Doppler. If you send a tone, you don't get information about delay. If you send one of these guys, you actually get information about both. All right, so now I have to tell you what a pulse in the delay-Doppler domain is. And straight away, maybe you object because you say there's no such thing as a pulse in the delay-Doppler domain, because there's something called the Heisenberg uncertainty principle. And Heisenberg uncertainty says that you can't localize in delay and Doppler. So what on earth are you doing? What we're doing is we're cheating. How do we cheat? So what we do is we create a lattice. So there's a delay period, tau p, and a Doppler period, nu p, and they define a box. We put a pulse inside the box, and then we extend it quasi-periodically in delay and in Doppler. So now we're not violating Heisenberg uncertainty because we're not improperly localized. And if you're a wireless engineer, we say the following. We say, you're a wireless engineer. You understand what your Doppler spread sort of is, and you understand what your delay spread sort of is. And we're going to invite you to choose the delay period and the Doppler period so that the delay period is bigger than the Doppler spread, and the Doppler spread, and the Doppler period is bigger than the Doppler spread. Okay? But now I have to tell you about how you get from the delay-Doppler domain to the time domain, because we transmit time domain waveforms. We don't transmit Doppler domain waveforms. So here we are. We've got our little pulse. And here I have to say that, we start with the Dirac delta, and then we apply something like a sinc filter or a product of sinc filters or a product of root raised cosine filters. And so we get something with a support in delay and Doppler. So here, support in Doppler is 1 over t. Support here in delay is 1 over b. How do we get from the delay-Doppler domain to the time domain? We apply a transform. What's the transform? It's the Zak transform, the inverse Zak transform. And these are mathematical details that are buried in the paper. I'm not going to go through them. What happens here is that the duration of the signal is basically t, and each of these little pulses has width 1 over b. So that's how the structure of the time domain waveform is related to these two quantities. The waveform itself is a pulse train. The different pulses are separated by the delay period tau p. And the position of the pulse in the fundamental period tells you, the delay thing tells you about the offset, and the Doppler thing tells you about the modulating tone. Now, if there are people in here from the quantum workshop, this is actually very much like GKP states. In fact, you can sort of see the torus, because if you actually move this by certain discrete intervals, you'll get back the same thing. And if you move the Doppler thing, you'll get back the same thing. So we're sort of living on a torus. Oh, and we're always going to look at underspread channels. So tau p times nu p is going to be 1. We can talk about how to get around that, but for now, we're just going to do that. All right, so now, what do radar engineers do? Let me unfairly characterize what radar engineers do. So radar engineers, they have a waveform S, okay? And they form something called the ambiguity function. The ambiguity function is about what it's difficult to see. So they take S and they displace it in delay, and they displace it in Doppler, and they take the inner product with the original function. They take the absolute value and they square it. That's the ambiguity function. And here, what I've done is I've shown you the ambiguity functions of a time domain pulse and a tone. Okay. And you can see that we get good resolution in one direction and lousy resolution in the other direction. And this was something that Woodward knew, and he didn't like so well. And Woodward came up with this idea in 1953. So Woodward was actually doing GKP states in 1953. Because you see here, what Woodward's idea was, when I just transmit a narrow Gaussian, I get this ambiguity function. If I have a train of narrow Gaussians that's modulated by a wide Gaussian, then this ambiguity function breaks up into a lattice. And this has advantages for figuring out what the radar channel is. So that's a beautiful idea. And if you think about this structure, this looks very much like our pulsone structure. And it motivates the idea of using the pulsone for both sensing and communication, which is a big thing in 6G. And this is what happens. This is the ambiguity function of a point pulsone. You see it has the same lattice structure, the delay period and the Doppler period. That's telling you about what you can resolve. One of the things that I would suggest here is that if your radar engineers love tones, they love chirps. They do up chirps, they do down chirps. The ambiguity function of all those things are lines. And they do an up chirp and a down chirp, and they meet, and that's where the target is. Now, the problem is that if they have like 4 targets, and they draw these lines, there's some of them are targets and some of them are ghosts, and it's really quite difficult to figure out which is which. And what I suggest in this picture is that lattices plus lines have to be lines in terms of resolution. Okay. All right, now, we have these pulsones, these pulses in the delay-Doppler domain, which are quasi-periodic functions mathematically. And I want to give you an idea of how these doubly spread channels, which are accumulations of reflectors, how they act. The mathematical way in which they act is something called twisted convolution. You guys all know what convolution is. Twisted convolution is like convolution just with phases, right? It's not intrinsically more difficult. We identify something called the crystallization conditions, which is exactly that the delay period is bigger than the delay spread. Doppler period's bigger than the Doppler spread. And what turns out is that the So here, all right, let me, so here I say, the interaction of a doubly spread channel with the pulsone is predictable and geometric. Predictable means I send a pilot, I measure the response, I know the channel at every point in this subframe. Okay? That's what it means to be predictable. Right? If you're a machine learning algorithm, what do you want? You want predictability. Actually, why do you like the delay-Doppler domain? Right? Because you want to buy time for signal processing. You want to buy time to move functions like scheduling to the cloud. How much time can you buy? Well, you can't do better than the speed at which the reflectors change. But if you're operating in the delay-Doppler domain, you are meeting that lower bound. When you operate in time frequency, when you do OFDM projections, those representations are varying much faster, and you have a smaller time horizon. Okay, now, if you do wireless, you're used to thinking about things like fading. One of the messages of this talk is there's no such thing as fading. And let me explain what I mean by that. So fading is all about aliasing in the delay-Doppler domain. So here, I've tried to draw a picture of unpredictability. Okay, so here, the Doppler spread is not less than the Doppler period. And so if you're in this area, you actually feel this and that replica. And in fact, what happens to you is some linear combination of those two things. And if you were over here instead of over here, it would be a different linear combination. And you can't predict this linear combination from that linear combination. And so that's aliasing. I mean, you guys all teach signals and systems. So aliasing is a very familiar concept. Fading is just aliasing in the delay-Doppler domain. This is what happens when you don't have any aliasing. You can read off the channel from response to a single pulsone. You know the input-output relation everywhere in the channel. And here I want to make a distinction between channel and input-output relation. I don't care about channels. In fact, all of the examples that you see here are going to be vehicular A channels for which you don't have enough time or bandwidth to resolve the channel. Okay? Because I don't care about channels. What I care about is an input-output relation that is predictable. Right? That's the key thing. Yeah, so this is just a picture of know what happens at one point, you know what happens at every other point. This is this little thing that we use for twisted convolution. And okay, if you're an algebraist, you should really like twisted convolution because it simplifies everything. It's associative. And what that means is that you can have receive filter, you can have channel. So you can have transmit filter, you can have channel, you can have receive filter. They all act by twisted convolution. Twisted convolution is associative. So you have a very simple relation between your inputs and your outputs. And that's, in a sense, the power of algebra. So this is a picture. You're operating in so here, this picture here, where you've got time selectivity. Why do you have time selectivity? It's because you had aliasing in Doppler. The Doppler period was really small. Over here, you have frequency selectivity. Why do you have frequency selectivity? Because you have aliasing in time. When you don't have any aliasing, and you bring everything back to the delay-Doppler domain, everything has the same energy. What you've produced is a little Gaussian channel. Two-dimensional Gaussian channel. Long time ago, I used to work on modems. I love Gaussian channels. So this is a great thing. This is about predictability of the I/O relation. So here we sent a pilot here, and we tried to predict what the effect was on every one of these pulsons. And green is pretty good, yellow is less good. So you see, if you're in this regime, you're very predictable. Actually, one of the things I forgot to say before, but I should really have said, is maybe you're looking at this and you're wondering, okay, you're using these funny functions. Have you actually given up anything in terms of like Nyquist criteria? These pulsons are kind of a spanning set, a basis. I think they're almost orthogonal for functions that are limited in time and limited in bandwidth. And it's actually really easy to see this. I think it's actually it's a nicer demonstration of the fact that you can achieve the time bandwidth product than the original proof of Slepian, Landau, and Pollock. So just wanted to. You might have been, thinking, all right. You might have been thinking, okay, so you have this funny Zak transform, and I don't really understand the Zak transform. I sort of understand the Fourier transform. Have you done something? Have you snuck in something that's just much more complicated? The answer is no. You know, there's like time, frequency, delay, Doppler. There's transforms that take you from one into the other. At the end of the day, they're all little Fourier transforms. One is not more complicated than the other. Here, what's interesting? So here, I'm going to show you some curves. So I said it's not a math talk. I'm showing you some curves, and then qualitatively, I'll tell you about the curves. So here, I'm giving everyone the benefit of perfect channel estimation. I have a particular channel. These are the statistics of the channel. And here, I'm varying the dimensionality of the window. You know, I can have windows with different aspect ratios, and by varying the aspect ratio, I can make it more like TDM or more like FDM. And so the TDM and FDM, those are the red curves. These are different things. This is the Zak modulation and the crystalline regime. So, summary. You want to operate in the crystalline regime. You approach TDM as the delay period gets bigger. You approach FDM as the Doppler period gets bigger. All right, so here, this is my propaganda about channels. Don't care about channels. You want to win math prizes, you work on estimating channels. You want to build a scalable wireless system? Throw channels out of the window. You don't care. Right? What you care about is constructing a manifold which is stable and predictable. You don't care how that manifold arose. So here, here, this is the one exception to the vehicular A model. I made a toy model where the delay shifts are like integer multiples. It's a really easy channel to learn. And Zak learns the channel as well as it can be learned. But if it doesn't try to learn the channel, if it just does this model-free, reading off the effective channel taps from the response to a filter, it does really well. My point of view is that when you think about scalable wireless systems, you want to have something that's low complexity like that. It is not a scalable solution to give every user their own NVIDIA or GPU, right? I mean, You want to do simple things. All right, when it's not possible to learn the channel, so here it's not possible to learn the channel because we don't have enough bandwidth, we don't have enough time. Zak-OTFS is still trying. It's not doing very well. But when it's just reading off, it actually does almost as well as perfect information. You can mess with the filters and you can improve this. So root raised cosines are better than sinks. You can think about the impact of Doppler because you want to have some kind of system that is resilient to large Doppler spreads. And what we're showing here is that if you're well inside the crystalline regime, you are super resilient. So that's a useful thing because you have to have one thing that works for everyone. You can't be figuring out how fast they're moving and then doing something special. This is a slide to say that if you're interested in interoperability between different sorts of channels, you can choose the dimensions of the period box to make that work. Even like satellite and mobile. All right. Here's the point. Here's the slide for algebraists. So this is this twisted convolution. And we say, oh, this is the input in the delay-Doppler domain. First, we applied a transmit filter. Then we applied a channel. Then we applied a receive filter. Each time we act by twisted convolution. Twisted convolution is associative. And so the result is some effective channel, twisted convolved with your input. And you learn H. Okay? You can learn H. And after you've learned H, everything is predictable.
Can we think of H as a smooth version of the original channel because those are two filters?
Yeah, you can think of it as an effective channel. Right?
It's like simpler to learn because it's smooth.
Yeah, I mean, so it's the thing that you want to learn because it connects inputs and outputs. Now, there's another version of OTFS, and I suppose I should tell a story because I'm looking at Emanuele and I'm going to explain that you have to be way more mathematically sophisticated to work on this version. And I'll explain how this version came about because actually on the first slide I said I was an advisor for Cohere Technologies who pioneered this way of signaling. And their first hope was to get their waveform into 5G. And they weren't really communication theorists, and they were sort of naive. And what they thought was, we'll show up at the standards and we'll say to Ericsson, you know, we have a better waveform. And Ericsson will look at them and they'll say, oh, you know, you do have a better waveform. Let's use your waveform. Well, that didn't happen. Ericsson said, we like our waveform, please go away. And they had tried to make this work by realizing Zak-OTFS as an overlay on OFDM. And you can do that, but when you do that, it's a mixture of periodic and quasi-periodic signal processing, and it's really hard to untangle. You can do better, but it's hard to untangle. And in fact, here I've shown what does it mean to be hard to untangle. I've compared predictability. So on the left hand is Zak, and on the right hand is multi-carrier OTFS, and you can see that's blue. That's yellow. One is more predictable than the other. You can compare to, I mean, people, actually, I think Emmanuel is one of them, who have shown that MCOTFS is better than OFDM. So I'm not going to say anything about that. I'm just going to take it as given. Zak is better than MCOTFS. I'm not going to say very much about this, but it's a great quote from George Orwell. He says, every generation imagines itself to be more intelligent than the one that went before and wiser than the one that comes after. And so here we've got a progression of standards. And every time we switch, like when we switch from CDM to OFDMA, we don't regret the fact that we switched because we calculated that the benefits of being able to adapt instantaneously outweighed the benefits of spreading. But I would say that what Orwell is telling us is that we should spend a little time looking back, thinking about what we've lost. And there were some things that we liked about CDMA. I mean, it was noise-like. The things that we didn't like, because we couldn't equalize it, because the way that we spread the signals had nothing to do with the channel. However, there's a domain that we have not explored. That domain is making filters in the discrete delay-Doppler domain. And I'm not going to talk about that. But I have explained how OTFS kind of, you can move along the period curve, tau p nu p equals 1, and you can move from single carrier to multi-carrier. You can actually also move in this direction by applying filters. The other thing that I like about this is it turns wireless into geometry. When you're thinking about how do you figure out the channel from the response, that's all about ambiguity functions. And the ambiguity functions are supported on lattices. So it's all about lattices. Right? I like lattices. So, conclusions. It's 40 minutes, almost. So, bad news. It's becoming impossible to learn channels. Good news, you don't have to. In the crystalline regime, you can do model-free operation. And I want to just make the point, right? Model-free operation means that you can decide on a Zak-OTFS subframe, which is like 1 millisecond, in a millisecond, right? You're not running some big, deep neural network for a long time doing something. It's working at the speed of wireless. And we, of course, are zealots. I mean, we believe in signal processing in the delay-Doppler domain. But I hope I've convinced you that you should explore the delay-Doppler domain. And that's my last slide. Pulsons in the crystalline regime. Live here, you must. There you go.
Thank you very much. We have some questions. Maybe I'll start. I have this question that is related to information theory. So sometimes when you set up a system where you can learn something, it costs you an information. And it seems like here, in the regimes where you can't learn the channel but you can still transmit, you're actually perhaps even improving the information theoretic limit, in the sense you can't estimate the channel, then you could get more data. Have you guys thought about this?
Not a whole lot. I mean, some things that I will say is, if you're worried, so when you're thinking about capacity, right, I've just shown how you can think about a wireless channel as a two-dimensional Gaussian channel. That's actually, OFDM is not like that, right? When you do something on one tone, I mean, you can't do things uniformly. So getting to capacity, information theoretically, is easier in this world. The other thing that I would say is and I haven't talked about it at all here, is integrated sensing and communication. In a sense, what's happening here is separate sensing and communication. We're doing sensing in one subframe, we're doing communication in the other. And so when we think about information theoretic optima, we're going to have to do them both in the same subframe.
All right. questions?
Could you maybe comment a little bit about the implications of this to coding? So, for example, you talked about transmitting completely in time. And if you have a frequency selective channel, then you end up with intersymbol interference and you need complicated equalizers. But from a coding perspective, then you end up needing to design a code for a channel with memory.
So what I would say is organize yourself so that you don't have aliasing. Or so that you have aliasing that is very controllable. And because I don't want to worry about that. I don't want to do that. Actually, what I would say, papers that I would like to write. Here's a paper that I would like to write. There you go. I'd like to write a paper which is about rehabilitating OFDM. I know how to rehabilitate OFDM to take care of exactly those issues. And it has to do with controlling aliasing.
All right, thank you very much.